Okay, we've seen that for power functions, we conjecture at least that there's a sweet spot for power functions. That is, there exists some y factor with the property that the slope graph of the power function is a straight line, is linear. Now, we've explained what that means, so I'm just referring back to that to give us a little context for exponential functions. Okay, there's a sweet spot associated with the base of an exponential function, and we're going to develop that idea. First of all, if our doubling distance is indicated by the arrow here, and if we just start at some point on the x-axis for a function y equals b to the x, well, the point on the y-axis is for x equals 0, so that the y value is b to the 0, which is 1 for any value of b. So we know that the y coordinate here is 1. We don't know what the doubling distance is. That's undetermined. And we're going to play around with the doubling distance to find a doubling distance that hits a sweet spot of a slightly different kind. Okay, obviously we can't define the sweet spot for the exponential function the same way we did it for a power function, because we got a completely different way of constructing the function, a completely different function here. Okay, well, if this is the doubling displacement, then of course the x value is going to double between here and here. It's going to double again between here and here, so that this is going to double. It's going to put us up about here, and then this one's going to be up too high to reasonably graph. If we go the other direction, this point has to be twice as high as this one, because between here and here the y value has to double. And similarly between here and here, this point has to be twice as high as this point, meaning this point here is going to have half the y coordinate of this point, and we're going to get our characteristic graph of an exponential function. Now I want to focus in a little bit on just what happens in here, close to the origin. So I want to redraw this graph, but slightly, or maybe not so slightly, expanded. So I've got the point 0, 1 here. So this is in fact the point 0, 1. We've got our doubling distance, which I'm going to make a little longer now than it was before, so that at this point we're going to be at this point over here, we're going to be half as high as we were here, so we're going to have this. So we know that the y coordinate is 1/2, right? So, and then over here we're going to double the y coordinate, so we're going to have a y coordinate of 1. And our graph is going to kind of look like this. Now, as when we talked about a sweet spot for the power function, and we talked about the way the slopes behave, we want to talk about the way the slopes behave here. And there are 3 important slopes. First of all, we have the slope of the tangent line at this central point here. So there's our tangent line. And if we draw a little triangle here, we can get an idea of what the slope of the tangent line might be. Okay, if we go from this point to this point, we have a chord. And if we go from this point to this point, we have another chord. Okay, so we have 3 slopes. Now, we're going to call the slopes, I'm going to label them 1, 2, 3, so I'm going to label them A, B, C. I'm going to label these line segments A, B, and C. So I can say that slope A is less than slope B, which is less than slope C. Okay? That's a badly written S. Okay, I'm going to add a little bit of notation here. The doubling distance it's a little unfortunate that I've used A, B, and C here for the three tangent lines, and I want to use D for the doubling distance because I've done that before. So the letter here has a meaning different than the letters here. I might come back and change that and do a little bit of revision, but let's go with it the way it is. Okay, so the rise for slope A, okay, well, let's see, let me just pose this as a question. In terms of the doubling distance D, what is the slope A and what is the slope C? Okay, well, pause a minute and see if you can write down an expression for slope A and slope C. It's worth thinking about for a couple of minutes, so I would pause and think about this. Now, hopefully you've done that, and maybe you made some progress, and maybe you didn't, and maybe you gave up before you started. Got 2 pieces of green chalk in my hand. Okay. Well, for each of these questions, what's the rise and what's the run? What's the rise for segment A? What's the rise for segment C? What's the run for segment A? What's the run for segment C? Now, in trying to answer the question, what's the expression for the slope, you would want to naturally break that question down into 2 simpler questions, which is, what's the rise? What's the run? So anytime you want to determine a slope, you ask yourself, well, what's the rise and what's the run? Then you're not trying to do a whole slope, you're just trying to identify rise and run. You might or might not be able to do that, but okay. So, again, stop and think for a minute. There's a fairly obvious answer to what's the rise and what's the run. Okay, well, let's answer the simpler question. What's the run between this point and this point? Can you tell me what the run is between here and here? That is, if we had a triangle that went from here over to here, what's the lower side of the triangle, the horizontal triangle, horizontal side of the triangle? And what if we had a triangle from here to here? So we do our basic triangle like this one. What's the run? Okay, well, it should be pretty clear that the run is D. Okay, so the run of each of these triangles is D. So, it should have a damp place on here to, that's not as clear as I like it. And I do want to keep it clear, so let's try once more. Okay, and I'm going to go ahead and clear out the questions for the rise as well. Okay, so, well, from here to here, what's the horizontal distance? It's D. So the run in both cases is D. The doubling distance. I've got to come up with a better notation for doubling distance, but haven't been able to think of one that I think would work better for you at this point. Okay, well, now, what's the rise for this one? What's the rise? Okay, you should stop and think. It should be pretty obvious. Okay, little hint. This is 1 unit here, right? And what do we know about doubling distance, and what do we know then about the y-coordinate of this point? And as far as that goes, the y-coordinate of this point. You should stop and think for a minute. Much better if it occurs to you without me telling you. But I'm going to go on now. Hopefully you stopped and thought about it. Hopefully you've got it. Okay. Well, this is the doubling distance. If the y-coordinate here is 1, then the y-coordinate here, when doubled, has to be 1. So the y-coordinate here has to be 1/2. So when the rise is from 1/2 to 1, that means the rise is 1/2. And what about from here to here? Well, here's the doubling distance, so the y-coordinate doubles from 1 to 2. From 1 to 2, the rise is 1. Okay, so now what are the expressions for the slopes of the two segments? You should be pausing while I'm doing this, or you should be thinking about it. Pause until you think you have an answer. But it's rise divided by run, and that's going to be 1/2 divided by d. That's 1 over 2d. And here it's 1 over d. So now we can say that the slope at B is greater than the slope at A, which is 1 over 2d, and less than the slope at B, which is 1 over d. And this is the slope of the tangent line. Okay, so we have this pretty neat inequality for the slope of the tangent line. Now, I'm going to assert that if D is, well, I'm going to make those assertions in a different video. We're running short on time on this one. It's going to take me longer than I have. Okay, well, I'm going to give a quick synopsis of this video, and then we'll go on and let me pose the question I was going to pose here.